Hello, welcome to this lecture video. So today we will be talking about run test of randomness. So for run test of randomness, it is a non-parametric test used to know the randomness in data. So run test of randomness is also called Geary test. So we use this to check if our data is randomly encoded or the order is random or not. So to do this, of course, let me show you first the assumptions in run test of randomness. So in terms of the data level, it is assumed that the data is recorded in order and not in a group. So if data is not in order, then we have to assign the mean, the median, or the mode value to the data. So this mean, median, and mode can be used now to be basis whether the number, if how many numbers of data is below to the value of mean, the median, or the mode, or how many values are above the mean, the median, and the mode. For the data scale, in run test of randomness, it is assumed that the data is in numeric form. So this condition is compulsory in run test because in numeric data, it is easy to assign run to the numeric data. So this is actually one of the requirement even in other tests. So as much as possible, when we encode our data, it must be in the numerical form. Even if later our data is not numerical, just like ordinal or nominal, the data that must be encoded is in numeric data. For the distribution, so run test of randomness is a non-parametric test. So obviously, we don't need to check whether it is normally distributed or not. So it does not assume any assumption about the distribution. And in run test of randomness, of course, the probability of run is independent. Okay, so these are the reference materials for this discussion. And of course, we are now ready to show you how to generate the result using SPSS. So we have to go to our data set. So where is our data set? So this is our data set. So it's the same data used in the paired sample t-test when we actually execute also or generate the result. Except that I added here 6. So also to have an example of nominal data. So our assumption here is that our data is of course randomly is ordered, or the order is random rather. So analyze. So how to do that? Click analyze, non-parametric test, and we have to go to run. So we have here run. So we have to click that. So if we will be, for example, by default, so let's reset this so that you can see the default. Let me first classify the measure of sex. So this is, of course, nominal. Again, let's repeat. Analyze, non-parametric, and then let's move to runs. Let's start with sex. So I'll transfer this test variable list. So if you notice here, there is a cut point. So this will be the basis now of identifying what is the less than, what's the greater than, how many numbers are less than or greater than this number. Now, looking at the values here, what we use is 1 male and 2 female. For us to determine how many males are above and below the cut point, the number that we have to use as cut point is in between 1 and 2. Because later, if we will be just using 1, obviously, the number below is 0 and the number above it will be equal to the number of 2. So as as explained, what we need to use as cut point is the number in between this data or coding scheme that we use. So this is 1 and 2. So we will be using 1.5. But we will also show you what will the result be if we check the median, the mode, and the mean. And of course, custom. And this is where I place 1.5 and then click OK. So these are now the result. So as you can see here, if we will be considering the first one, the median. So this is 1. The test value is 1. The highest is 1. It means, so what the number less than 1 is of course 0 as mentioned. And greater than or equal to the number 1 are all the data. So that is what we can generate. So which means it's not that useful at all if we will be considering the median. How about if we consider the mean? So considering the mean is 1.43. So anyway, the value is in between 1 and 2. That's why the value less than it is 17 and greater than it is equal to 13. So usually what we are doing is to add that the two data, our numerical or our categorical data, which is nominal, and then divide it into 2. So that's 1 plus 2 is equal to 3 divided by 2 is 1.5. That's why what we used or what value we use in custom is the 1.5. So let's go back here. So the number of runs is 10. Total cases is 30. And asymptotic significant is 0.048. So which means it is significant. So our data is random. And let's move again. So here, similarly with our first data, we're in, of course, the mode is 1. And then for the last one, so this is our data. So the test value is 1.5. The total cases is 30. The number of runs is 30. Asymptotic significance is 0.048, which is, of course, similar to the value of mean because, of course, the number that we used is in between 1 and 2. So we are expecting for the result that will give us also 0.048. Now, how do we determine the number of runs? So we can go back to our data set and let's see. So it's actually counting for the number of changes in our data, just like, for example, here, 1, 1, 1, 1. So this is counted as 1 run, 2 runs, 3 runs. Again, it go back to 1. 4 runs, 5 runs, 6 runs, 7 runs, 8, 9, 10, 10 runs. So as you can see, it's actually the change in our data. So of course, if we're going to do it alternately, let's see how it works. So we are expecting for 30 runs if it's an alternate 1 and 2. So let's just verify for that. Okay, let's do it. So let me name this as sext 2. So let's analyze non-parametric test, legacy dialog, and click runs. So first, we know that this is a nominal data. Let's place it there. I'll remove all other values. I'll just use the custom 1.5 and click OK. So since we have the two values, as mentioned, since I changed the values alternately from 1 and 2, 1 and 2, the number of runs now in the sext2 is 30. And originally, we also present the number the number of runs or in our original data, and we counted that, and the result is 10. So it is randomly assigned, or the order is random, because the p-value is less than 0.05. So this ends this video. Thank you for watching.